Hi! In this chapter, we are going to discuss the solutions to differential equation. But first, we must define what a differential equation is. Try to Google it. A differential equation is said to be a mathematical equation that relates some function with its derivatives. In applications, the functions usually represent physical quantities wherein the derivative represents their rates of change, and the equation defines a relationship between the two. Because such relations are extremely common, differential equations play a prominent role in many disciplines including ours, which is the engineering discipline, physics, economics, and biology. Now then, why do we need to study differential equation? And why do we need to discuss solutions in differential equation? Many laws governing natural phenomena are relations, involving rates at which things happen. By using differential equation, we will understand or deeply understand the relation at which a given rate of change is happening. So to be able to investigate problems in fluid mechanics, circuit design, which is our major, heat transfer, population, or conservation biology, we must study differential equation. If you're going to ask me if the differential equation is easy to be solved, some are not, but many are easy to be solved. If you're asking me, what do solutions look like? Solutions are functions, so if expressed symbolically, they look like mathematical formulas, or geometrically, they are curves. Now, we go on to our topic, explaining the types of the solutions for differential equation. For the types of differential equation, we are going to concentrate on linear constant coefficient differential equation, or the so-called second order or higher homogeneous linear equation with constant coefficients. There are two types in solving differential equations. First is the classical method. The classical method comes in the general form where the linear constant coefficient differential equation is equal to P of t y double prime plus Q of t y prime plus R of ty is equal to G of t. We assume all coefficients are constants, a, b, and c. When G of t is not equal to 0, the equation is said to be non-homogeneous. But if it is equal to 0, it is a homogeneous equation. We must also take note that the classical method in solving differential equation uses the principle of superposition, whereas if y of t is an equation, then y sub 1 of t and y sub 2 of t are two solutions to a linear homogeneous differential equation, then so y of t is equal to constant y sub 1 of t plus constant 2 y sub 2 of t. If the two solutions to a linear second-order homogeneous differential equations are said to be enough, then the general solution to the linear second-order homogeneous differential equation can be easily calculated. Steps of solving differential equation using classical method. First, we must seek for the homogeneous solution x sub h of t. Then, for the particular solution, x sub p of t. Given that it uses the superposition principle, the total solution is equal to x sub h of t plus x sub p of t. Now, we will calculate the homogeneous solution. First step is to make g of t equal to 0. Given an equation, x double prime plus 3x prime plus 2x is equal to 1 plus t. Replace all the ddx function or the derivatives into m variable, making it m squared plus 3m plus 2 is equal to 0. Solve for the values of m, by taking the roots of the quadratic equation made by the replacement of the ddx function into m. The assumed homogeneous solution is based on the values of m, whereas m is equal to -2 and -1. If the roots of the solutions obtained is real and distinct, we must assume that x sub h of t is equal to a e raised to mt, whereas given the following equation, x double prime plus 4x prime plus 3x is equal to 0 and m is equal to -1 and -3, the homogeneous solution will be a1 e raised to -t plus a2 e raised to -3t. Plugging the values of m to the given equation a raised to mt. Otherwise, if the roots are real and equal, we must assume that x sub h of t is equal to a sub 1 e raised to m sub 1 multiplied by t plus a sub 2 e raised to m sub 2 multiplied by t. For example, if the equation is equal to x double prime plus 4x prime plus 4x is equal to 0, and the replaced equation is equal to m squared plus 4m plus 4 is equal to 0, we will obtain a value of m equal to -2. Therefore, the homogeneous solution will be equal to a sub 1 e raised to -2t plus a sub 2 e raised to -2t. Lastly, if the roots being calculated is a conjugate root or a complex conjugate root, we must assume that the homogeneous solution is equal to a sub k e raised to m sub 1 multiplied by t plus a sub k plus 1 e raised to m sub 2 multiplied by t, where m sub 1 and m sub 2 are complex numbers having real and imaginary part. For instance, if we're given an equation x of double prime plus 4x prime plus 5x is equal to 0, we will obtain m squared plus 4m plus 5 equal to 0. Using the quadratic equation and using the quadratic formula, we will get a root of -2 plus or minus I. Plugging the value of m to the given assumption of the homogeneous solution, we will get a sub k e raised to -2 minus it plus a sub k plus 1 e raised to -2 plus I multiplied by t. Given that equation, we must convert the complex formula or the complex values into its trigonometric equivalent, wherein the complex numbers being substituted to the value of m must have a value with the sine and a cosine part with its angle given as omega t plus alpha. Alpha can be calculated using theta for quadrant 1, pi minus theta for quadrant 2, pi plus theta for quadrant 3, and 2 pi minus theta for quadrant 4. The homogeneous solution given a complex conjugate root is equal to x sub h of t equal to a subtotal e raised to sigma multiplied by t sine omega t plus alpha, wherein the a subtotal will be calculated using the formula given to the right of the slide, and the alpha will be calculated using addition and subtraction within given reference. For example, if the theta being calculated is located in the first quadrant, it is going to be our alpha. But if it is located in the second quadrant, we will substitute it through the equation pi minus theta to get alpha. The same thing as quadrant 3, theta will be added to pi to get our alpha. And for quadrant 4, 2 pi minus theta is equal to our alpha. given to be calculated, theta is equal to the tangent inverse of the constant being calculated in the homogeneous solution. In continuation, as I have said earlier, in doing classical method, we must take the homogeneous and the particular solution in two different ways. After getting the homogeneous solution, we must now obtain the particular solution. The assumed particular solution is based on the form g of t, whereas the g of t is given on the table below. If g of t is a sinusoidal, therefore it is equal to r cosine omega t plus phi, wherein this equation is equal to r cis of phi. The particular solution x sub p of t is equal to constant e raised to I beta. The values of the coefficients of x of p can be solved by substituting x sub p of t, the value of the derivative or the ddx function, and the d raised to n to the original differential equation. Once you solve for the coefficients of the particular solution, get the total solution x of t total by adding the homogeneous solution to the particular solution. Do take note that coefficients of the homogeneous solution are still unknown. If initial conditions are given, the coefficients are solvable. If it's given, substitute it with the equation to get the values of the coefficients. Now, to further understand the classical method, I will be giving you an example. Given an equation, x double prime plus 4x prime plus 3x is equal to t plus 1, wherein dx of 0 is equal to 0 and x of 0 is equal to 1. First, get the value of the classical method homogeneous solution, or x sub h of t, by replacing the given equation and the dds function by m, obtaining m squared plus 4m plus 3 equal to 0. Therefore, by using the quadratic equation, we will get the value of m equal to -1 and -3. With this, the roots can be said to be real and distinct roots. Given a root which is given distinct and real, the homogeneous solution is equal to a sub 1 e raised to -t plus a sub 2 e raised to -3t. For the continuation of our solution, we must obtain the particular solution x sub b of t. Assume x sub b of t is equal to constant multiplied by t plus a constant, which can be seen in the right side of the given equation earlier. Get the values of dx sub p of t and d double prime x of p of t, wherein dx of p of t is equal to a and d squared x of p of t is equal to 0. Substitute the values to the original equation and solve for a and b. x double prime plus 4x prime plus 3x is equal to t plus 1. Substituting the values, 0 plus 4a plus a multiplied by t plus b is equal to t plus 1. Given t raised to 0, 3a is equal to 1. And given t is 1, a plus b is equal to 1. Obtaining the value of a equal to 1/3 and b equal to negative 1 over 9. Therefore, x of t is equal to 1/3 t minus 1 over 9. Since we know already the value of the homogeneous solution and the value of the particular solution, we must use the superposition principle to get the total solution of the differential equation using classical method. X subtotal of t is equal to a sub 1 e raised to negative t plus a sub 2 e raised to negative 3t plus 1/3 t minus 1 over 9. Since the conditions are given earlier, we will obtain the value of a sub 1 and a sub 2. After obtaining the values of the homogeneous and particular solution of the classical method, we must now use the initial condition given recently, whereas x of 0 is equal to 1 and dx of 0 is equal to 0. The total solution of the classical method differential equation must use x of 0 is equal to 1 and must be equated to 1. Therefore, a sub 1 e raised to negative t plus a sub 2 e raised to negative 3t plus 1/3 t minus 1 over 9 must be equated to 1. By doing so, we'll obtain an equation a sub 1 plus a sub 2 is equal to 10 over 9. On the other hand, by using d of x 0 is equal to 0, we must get the derivative of the equation a sub 1 e raised to negative t plus a sub 2 e raised to negative 3t plus 1/3 t minus 1 over 9. Differentiating the equation, we will obtain negative a sub 1 e raised to negative t minus 3 a sub 2 e raised to negative 3t plus 1/3. Equating it to 0, we'll get an equation a sub 1 plus 3 a sub 2 is equal to 1/3. By using the equations obtained recently, we will get the value of a sub 1 and a sub 2, 3/2 and negative 7 over 18 respectively, arriving to the final answer, x sub t of t is equal to 3/2 e raised to negative t plus negative 7 over 18 e raised to negative 3t plus 1/3 t minus 1 over 9. For another example of the classical method, we will now have an equation with an exponential function equated to the right side of the equation. Given x double prime plus 6x prime plus 9x is equal to 3 e raised to 2t. Whereas the initial condition is equal to x sub 0 is equal to 1 and dx of 0 is equal to 0. First thing, we now get the homogeneous solution, replacing the derivatives into m, obtaining m squared plus 6m plus 9 is equal to 0. Using the quadratic formula, we will obtain the roots negative 3 and negative 3. Thus, the roots are equal and real. Therefore, x sub h of t, or the homogeneous solution of the given equation, is equal to a sub 1 e raised to negative 3t plus a sub 2 e raised to negative 3t multiplied by t. After obtaining for the homogeneous solution of the classical method differential equation, we must now obtain for the particular solution of the given equation. Assume x sub p of t equal to a e raised to 2t. Assume the x sub p of t is equal to 2a e raised to 2t. And assume x of p of t double prime is equal to 4a e raised to 2t. Upon assumption, substitute the values to the original equation and solve for the value of a. X of p double prime plus 6x of p plus 9x is equal to 3e raised to 2t. By substitution, 4a e raised to 2t plus 6 multiplied by 2a e raised to 2t plus 9a e raised to 2t is equal to 3 e raised to 2t. Thus, the value of a is equal to 3 over 25. Therefore, the particular solution, x of p of t is equal to 3 over 25 e raised to 2t. After obtaining the homogeneous and particular solution for the second example, we now use the initial condition d of x of 0 is equal to 0 and x of 0 is equal to 1. We now get x sub t of t is equal to x sub h of t plus x sub p of t, or the superposition principle. X sub t of t is equal to a sub 1 e raised to negative 3t plus a sub 2 e raised to negative 3t multiplied by t plus 3 over 25 e raised to 2t. Conditions are given. Find for the values of a sub 1 and a sub 2. By using x sub 0 is equal to 1, a sub 1 e raised to 0 plus a sub 2 e raised to 0 multiplied by 0 plus 3 over 25 e raised to 0 equal to 1, it will bring us to an answer for the value of a sub 1 equal to 22 over 25. Therefore, updating for the total solution, x sub t of t is equal to 22 over 25 e raised to negative 3t plus a sub 2 e raised to negative 3t multiplied by t plus 3 over 25 e raised to 2t. On the other hand, by using another initial condition d of x of 0 is equal to 0, we now get for the first derivative of the equation set earlier. X of t is equal to 22 over 25 e raised to negative 3t plus a sub 2 e raised to negative 3t multiplied by t plus 3 over 25 e raised to 2t. getting the derivative using differentiation, we will get negative 66 over 25 e raised to negative 3t plus a sub 2 multiplied by the group e raised to negative 3t minus 3 e raised to negative 3t multiplied by t plus 6 over 25 e raised to 2t. Substituting the value of t for the equation and equating it to 0, we will obtain the value of a sub 2 equal to 12 over 5. Therefore, our final answer will be equal to x sub of t is equal to 22 over 25 e raised to negative 3t plus 12 over 5 e raised to negative 3t multiplied by t plus 3 over 25 e raised to 2t. Moving forward for the third example of our classical method, we will have an equation involving trigonometric functions. Given the equation x double prime plus 2 prime plus 10x is equal to 3 cosine 2t, and the initial conditions x of 0 is equal to 0 and x of prime of 0 is equal to 0. First step, get the homogeneous solution of the given equation. It can be done by substituting the value of the primes by m, obtaining m squared plus 2m plus 10 is equal to 0. Using the quadratic formula, we will obtain the roots negative 1 plus or minus 3i. Therefore, the homogeneous equation or the homogeneous solution is equal to a sub k e raised to negative 1 plus 3i multiplied by t plus a sub k plus 1 e raised to negative 1 minus 3i multiplied by t. Upon getting the homogeneous solution, we will now get the particular solution of the given equation. We will assume x sub of p of t is equal to a cosine 2t plus b sine 2t. Assume the first derivative equal to negative 2a sine 2t plus 2b cosine 2t. Given that the derivative of cosine is sine and the derivative of sine is cosine, assume the second derivative equal to negative 4a cosine 2t minus 4b sine 2t. For the continuation of the solution, the obtained value of the x function, its first derivative and second derivative, will be substituted to the value of the given equation. Involving all the given, our main equation will be equal to negative 4 cosine 2t minus 4b sine 2t minus 4a sine 2t plus 4b cosine 2t plus 10a cosine 2t plus 10b sine 2t. It will be equal to 3 cosine 2t as the constant part of the equation. Combining similar terms, our final equation will be equal to 6a cosine 2t minus 4a sine 2t plus 4b cosine 2t plus 6 sine 2t is equal to 3 cosine 2t. Moving forward, in solving the equation, we will now combine all the variables involving cosine 2t. Our equation will be equal to 6a plus 4b is equal to 3. On the other hand, we will also combine all the equation or functions involving sine 2t. This will be negative 4a plus 6b equal to 0. Involving two equations and two unknowns, we will get the value of a and b equal to 9 over 26 and 3 over 13 respectively. Therefore, the particular solution of the classical method example number 3 is equal to 9 over 26 cosine 2t plus 3 over 13 sine 2t. Applying the superposition principle, we will now combine the homogeneous solution and the particular solution, thus giving us an equation a sub k e raised to negative 1 plus 3i multiplied by t plus a k plus 1 e raised to negative 1 minus 3i multiplied by t plus 9 over 26 cosine 2t plus 3 over 13 sine 2t. With that, conditions are given, we will find for the value of a sub k and a sub k plus 1. In solving for the value of the constants a sub k plus a sub k plus 1, we will use the initial condition given in the problem. First, where x of 0 is equal to 0, we will change and substitute 0 for all the values of t in the equation, resulting to a final equation a sub k plus a sub k plus 1 plus 9 over 26 equal to 0. Isolating a sub k plus 1, it will be equal to a sub k plus 1 equal to negative a sub k minus 9 over 26. On the other hand, using the first derivative of the equation as an initial condition, x prime of 0 is equal to 0, we will get the first derivative of the final equation that we have been obtained. Applying differentiation, the value will be equal to quantity negative 1 plus 3i multiplied by a sub k e raised to negative 1 plus 3i multiplied by t plus quantity negative 1 minus 3i multiplied by a sub k plus 1 e raised to negative 1 minus 3i multiplied by t minus 9 over 13 sine 2t plus 6 over 13 cosine 2t. Involving the initial condition, we will now equate it to 0. Thus, we will get negative 1 plus 3i a sub k plus negative 1 minus 3i a sub k plus 1 plus 6 over 13 as an equation number 2. Combining both equations and using the substitution method, we will solve for the value of a sub k and a sub k plus 1, equating to a sub k equal to negative 9 over 52 plus 7i over 52, and a sub k plus 1 equal to negative 9 over 52 minus 7i over 52. For the continuation, we will get a total by adding both a sub k plus a sub k plus 1. Given the values of a sub k and a sub k plus 1, we will now isolate the imaginary part and the real part of the equations. Applying the formula given in the initial slides of the PowerPoint presentation, a sub t or a total is equal to the square root of 9 over 26 squared plus negative 7 over 26 squared, obtaining a value of the square root of 130 over 26. For our angle, alpha will be equal to 2 pi minus arctangent of 9 over 26 over negative 7 over 26, equal to 5.6221 radian. With the value being obtained in the different solutions, we will now have our final answer equal to the square root of 130 over 26 e raised to negative t sine 3t plus 5.6221 plus 9 over 26 cosine 2t plus 3 over 13 sine 2t, thus concluding the classical method in solving differential equations. Moving forward, we will now use the Laplace method in solving differential equation. Given any linear constant coefficient differential equation, L y prime is equal to s y of s minus y of 0, and if the condition is L of y double prime, it will be equal to s squared y of s minus sy of 0 minus y prime of 0. As you can observe, the value of s being a variable in the equation will be having a decreasing order of exponent, while the value of y in the equation will be having an increasing value of order of differentiation. To solve for the differential equation, perform Laplace transform to the whole equation and get the value of y of s. After getting the simplified value of y of s, perform inverse Laplace transform to get the total solution. As a tip, you can use the table of Laplace transform in solving the Laplace transform of the different equation involved in the problem. The table of Laplace transform is being projected in the equations and in the board and the PowerPoint presentation. For our example, given an equation x double prime plus 2x prime plus 10x is equal to 5, and an initial condition of x is equal to 0 and x prime of 0 is equal to 0, we will get the Laplace transform of the given equation and isolate x of s. Since the equation is in second order, we will have a Laplace transform equal to s squared x of s minus x of 0 minus x prime of 0 plus 2s minus 2x of 0 plus 10x of s is equal to 5 over s. Combining similar terms, we will obtain s squared plus 2s plus 10 multiplied by x of s equal to 5 over s. Transposing x of s, we will have 5 over s multiplied by the quadratic equation s squared plus 2s plus 10. After obtaining the equation of x of s, we will now perform partial fraction decomposition. We will partially decompose the denominator of the given equation. 5 over s multiplied by s squared plus 2s plus 10 will be equal to a over s plus bs plus c over the quadratic equation s squared plus 2s plus 10. Equating to the constant, 5 is equal to a multiplied by s squared plus 2s plus 10 plus bs squared plus cs. There's a tip. You can use Heaviside method in solving this partial fraction decomposition. For s is equal to 0, 5 will be equal to 10a. For s is equal to 1, 5 will be equal to 13a plus b plus c. And for s will be equal to 2, 5 is equal to 18a plus 4b plus 2c. Given three equations, three unknowns, we will obtain the value of the constants a equal to 1/2, b equal to negative 1/2, and c equal to negative 1. Substituting it in the equation, x of s is equal to 1/2 over s plus negative 0.5s minus 1 over s squared plus 2s plus 10. After getting the Laplace transform of the given equation, we will now perform inverse Laplace transform. For 1 over 2s, the Laplace transform will be equal to 1/2. And for negative 0.5s minus 1 over the quadratic equation s squared plus 2s plus 10, the Laplace transform will be equal to 1/2 e raised to negative t cosine 3t and 1 over 6 e raised to negative t sine 3t. Having the values, we will now obtain the final answer. X sub of t is equal to 1/2 plus 1/2 e raised to negative t cosine 3t plus 1 over 6 e raised to negative t sine 3t. After these examples, we will now proceed in solving case problems involving solutions of differential equation. Prepare yourself and try to memorize the table of Laplace transform for easy reference of the notes and the problems being solved in the past slides of the PowerPoint presentation.
Finally, we're going to discuss a research paper that discusses the solution to differential equations. The title is The Comparison of Solutions of Second-Order Linear Differential Equations with Constant Coefficients by Marcel Abbas. The abstract mentioned that the author wants to compare the solutions of second-order linear differential equations with respect to the form of the right-hand side of the equation and to the form of initial or boundary conditions. In this research paper, he also stated that there are differential equations that can be solved by both the Laplace method or the classical method, or what he called here as the method of variation of constants. And there are differential equations that can only be solved via one method only. Given is the linear differential equation of second order with the following form highlighted in the He also stated that the differential equation can only be solved by the classical method if the function is continuous. On the other hand, the differential equation can only be solved with the help of Laplace method only when the initial conditions are given. The first problem is only solved using the classical method because of the conditions given below. It cannot be solved by the help of Laplace method. As what we have read, the author solved the differential equation using the classical method only. The next is the next problem is only solvable by the Laplace method because the function is not continuous as given in the problem. The last problem is an homogeneous linear differential equations of second order with constant coefficients, and the right hand side is said to be continuous, and luckily it can also be solved via Laplace transform. Please take time to read and check how the author solved the differential equations. As we can see here, the answers by using classical method and Laplace method yield the same result. Finally, what the author stated in his conclusion is that any dynamical systems, which are one of the main objects in the area of operations research, can be described by differential equations of various orders, which is frequently in the order of an nth order homogeneous linear differential equations with constant coefficients. What is also stated here is that looking for a reaction of the system on input function, students of automation or any person can solve such inhomogeneous equations either using Laplace method or classical method. Well, in regard to the form of the right hand side or the input function and on the type of starting conditions they have to know both ways of solving this kind of differential equations. As what we have seen earlier, these types of differential equations can be solved by both classical and Laplace method or just by classical method alone or Laplace method alone. Also, the author stated that in this contribution, we showed how such equation can look like and how to solve it. What we really appreciate with this research paper is that it can serve as a guidance to students of engineering or of automation or any person who wants to learn to solve differential equations, especially the form of an n-ordered homogeneous linear differential equations. Classical method can Classical method and Laplace method are both great tools to solve this kind of differential equations, but because of the research of the author, we can really reduce the time to figure out how to solve these differential equations by looking at the form of the right hand side of the differential equation or on the type of starting conditions. We also think that this research paper teaches its reader some of the basic solutions to differential equations. As what we can see here, for example, his problem 1, it can also give extra help to students that have a hard time or want to challenge solving these types of solution in this manner or form. Or this one in problem 2, and on this one